Usually, when we think about mathematics, there's this expectation of just like absolute uncompromising precision.
Right, like a locked vault.
Yeah, exactly. Like you type in the exact right code, the door opens. But you type in one wrong digit and, well, the door just stays shut. It feels incredibly binary.
It does. And I mean, it's a comforting way to view the world, really. We kind of crave the security of a pinpoint answer, especially when you're being tested on your knowledge.
Right. But if you step into the high stakes reality of the physical world, or say a really busy hospital ward, that obsession with exactness can actually blind you to some pretty catastrophic errors.
Oh, absolutely. It really can.
So if you're listening today, welcome to the deep dive, and we're going to think of you as the learner today, especially if you're gearing up for the TEAS or HESI nursing entrance exams. We're looking at something crucial.
Yeah, the often misunderstood skills of rounding and estimation.
Exactly. And our angle today is all about getting close, fast. This isn't just about passing a math test. This exact skill is like the literal difference between a successful nuclear physics experiment and a multi-million-dollar spacecraft just disintegrating in the atmosphere.
It sounds dramatic, but it's completely true. And to understand how these tools actually prevent disasters, we have to draw a hard line between rounding and estimation.
Because people use the terms interchangeably all the time.
All the time, which creates a ton of confusion.
Yeah.
Because they are fundamentally different operations. They serve completely different masters.
Okay, let's unpack this. Looking at the prep materials, rounding is defined entirely as a mechanical technique.
Yes, a technique.
It's the deliberate replacement of a number with a simpler, less precise value that sits within a defined distance of the original. So like you have 4.87, you apply a rule, you get 5.
Right.
But estimation is defined as a broader cognitive strategy. It's the skill of producing an approximate answer to a calculation without actually working out the exact answer.
Exactly. You round a number that already exists, right?
Yeah.
But you estimate a result that you haven't even calculated yet.
Oh, that's a great way to put it. So if we're cooking, is rounding kind of like an ingredient we prep, and estimation is the actual recipe we follow to get a quick meal?
Yeah, I love that analogy. Rounding is an algorithm you execute, but estimation it's almost like a defense mechanism you deploy.
A defense mechanism, I like that.
And, understanding that difference requires looking at this massive pedagogical shift that happened in math education.
Wait, like how they actually teach it in schools?
Exactly. For most of the 20th century, American schools treated estimation as just a fallback.
Like what you do when you forget your calculator.
Right. It was the rough math you did when you didn't have a pen. It was treated as inherently inferior to, like, the real math.
Just a lesser form of reasoning, like a quick guess just to tide you over.
But then, beginning in the 1980s, with the number sense movement, which eventually shaped standards like the Common Core estimation, was completely reframed.
How so?
Educational researchers realized that really proficient mathematicians, they don't just calculate blindly. They estimate before an exact calculation specifically to know what a reasonable answer should look like.
Oh, wow. So it became like a first-class reasoning skill.
Precisely. And that reframing is the key to these nursing exams. The test writers, they aren't just checking if you know how to multiply a random string of decimals.
Right, they want to know if you have the situational awareness to see if your answer makes sense in the real world.
Exactly. If you multiply two values and your calculator gives you something in the tens of thousands, a good estimator instantly recognizes a flaw, because they already mapped out that the answer should live somewhere around, say, 3,000.
It's about establishing boundaries. And if estimation is a primary strategy for sense-making, I mean, human beings have been obsessed with finding those boundaries for centuries.
Oh, yeah. We can trace this rigorous approach to approximation all the way back to Archimedes of Syracuse.
Right, around 250 BCE. And Archimedes didn't have the modern decimal system, so he couldn't just, punch pi into a calculator.
No, he conceptually trapped it.
Trapped it.
Yeah, what's fascinating here is he used inscribed and circumscribed polygons. So he drew a circle, and then he drew a hexagon entirely inside that circle.
Okay.
And then another hexagon entirely outside of it. He knew the perimeter of the inner hexagon had to be smaller than the circle's circumference.
Right, because it's inside.
And the outer hexagon's perimeter had to be larger. Then he just kept doubling the size of those polygons, from 6 to 12 to 24, all the way up to 96-sided shapes.
That is wild. So he just kept tightening the net around the circle until he could definitively prove that pi was greater than roughly 3.1408, but less than 3.1429.
Exactly. He didn't know the exact infinite value, but he knew exactly what neighborhood it lived in. Archimedes proves that estimation is not a lazy guess.
It's a defensible range.
Yes, derived from a method you can actually repeat and verify. You trade absolute precision for bounded certainty.
Bounded certainty. I love that phrase. And that actually brings up one of the most striking examples from our sources today, the 1945 Trinity nuclear test.
A Fermi problem. This is a classic.
Yeah, so physicist Enrico Fermi is standing at base camp when the first atomic bomb detonates, and he doesn't have, like, complex diagnostic readouts in front of him.
No, not at all.
As the blast wave approaches, he simply holds up these small, torn scraps of paper and just drops them.
Right, he just watches how far the atmospheric shock front displaces those scraps of paper as they fall.
Which is insane to think about.
It is. But the physical displacement is proportional to the energy of the blast. So from that momentary visual, in a matter of seconds, Fermi calculates the bomb's explosive yield at roughly 10 kilotons of TNT.
But, and here's my question, the specialized instruments took days to produce the actual figure, which was closer to 20 kilotons.
Right.
Wait, so Fermi's answer was technically off by half. How is that a successful math strategy for our learner taking a nursing exam tomorrow?
Well, in a vacuum, being off by half seems like a failure. But this introduces the crucial concept of order of magnitude.
Okay, order of magnitude.
Fermi got the scale of reality right instantly. He knew the blast wasn't 1 kiloton, and he knew it wasn't 100 kilotons. In emergency physics, and frankly emergency medicine, getting the power of 10 correct immediately is the most vital step.
Because it tells you what you're dealing with.
Exactly. The exact price of a car matters eventually, but first you need to know if you're shopping for a bicycle or a Ferrari.
Right. You need to know what vehicle you're looking at. And to achieve that kind of rapid scale checking on an exam, the sources detail a specific arsenal of strategies.
It's not just a matter of rounding everything in sight.
Definitely not. Like, for example, if I'm looking at a nursing problem where I have to tally up a patient's fluid intake over a shift, and the numbers are all hovering around the same value, say 98 millil, 105 millil, 96, 102, and 99.
Instead of laboriously adding those digit by digit, you use a strategy called clustering.
Cluster.
Yeah, all 5 of those numbers are huddled or clustered right around 100. So your immediate estimate is simply 5 times 100. You have a baseline of 500 millirelers in like less than 2 seconds.
That is so much faster. And the sources also detail a strategy called compatible numbers, which, I'll be honest, feels almost like bending the rules of math.
How so?
Well, if the problem asks you to divide 152 by 7, the rounding instinct is to change 152 to 150. But 150 divided by 7 is awful to do mentally.
Yeah, it's terrible because 150 and 7 are not compatible.
Right.
The strategy here dictates replacing numbers with nearby values that play nicely together in your head, even if they aren't the nearest round number.
Ah, okay.
So you look at 152 and 7, and you mentally shift it to 140 divided by 7. 14 divided by 7 is 2, so 140 divided by 7 is 20.
And boom, your estimate is 20, derived almost instantaneously.
Exactly. Then there is front-end estimation.
Oh, this one is aggressive. If I'm adding a complex set of numbers, like 4,382 and 3,910, I just look at the thousands place and ignore the rest entirely.
Let's drop them.
Yeah, 4,000 plus 3,000 is 7,000. It feels so weird to just drop all those trailing digits.
It is aggressive, but it serves a specific purpose, right?
Yeah.
It establishes a hard floor.
A floor.
Yeah. You know your final exact calculation cannot possibly be less than 7,000. If your calculator spits out 6,800, you know instantly you missed a keystroke.
That makes total sense. And finally, there is standard rounding-based estimation, which most people are pretty familiar with.
Right, where you round each component to a friendly value before computing. So like 47 times 62 becomes 50 times 60, getting you to a quick 3,000.
Okay, but all these strategies rely on the mechanical technique inside them, which is rounding. And here's where it gets really interesting. Because rounding is a mechanical algorithm, it requires a formal rule.
Right, it's not subjective. You can't just guess.
And the debate over which rule to use is surprisingly fierce. Because bad rounding rules create, like, systemic disasters.
They absolutely do. Most of us are taught the round half up rule in grade school.
Right. If a number ends in a 5, you round up to the next digit. So 2.5 becomes 3.
Exactly. It's easy to teach. It's intuitive to learn. The problem arises when you apply that rule to large data sets or, continuous calculations. It creates a massive systemic upward bias.
Because the numbers 1 through 4 round down, which is 4 digits. But 5, 6, 7, 8, and 9 round up. That's 5 digits.
Right.
So the scale is permanently tipped upward.
To correct that imbalance, Professional numerical standards, financial institutions, computer architectures, they all use a rule called round half to even, commonly known as banker's rounding.
Banker's rounding. Okay, how does that work?
When you hit a perfect tie, like a 0.5, you round to the nearest even number.
Meaning 2.5 rounds down to 2.
Correct, but 3.5 rounds up to 4 and 4.5 rounds down to 4.
Oh, wow.
Yeah, so over millions of transactions, roughly half of your 0.5s round up and half round down. The bias is completely neutralized.
That is brilliant.
When the IE 754 standard for computer arithmetic was established back in 1985, Baker's rounding was made the default. The devices we use every day execute this rule silently in the background.
And when institutions ignore these rules or, implement flawed ones, the consequences are staggering. The Vancouver Stock Exchange in 1982 is like the perfect cautionary tale here.
Oh, that's a mess.
A total mess. They launched a new composite index and set the starting value at 1,000. But the software constantly recalculating the index didn't round properly. It truncated.
Yeah, truncation just chops off the decimal tail entirely. If the value was 5.678, it didn't round up to 5.68. It just chopped it to 5.67. It always, universally, rounded down.
And they were recalculating this index thousands of times a day. Over roughly 22 months, that microscopic truncation error compounded with every single calculation.
Every single one.
By November 1983, the index had drifted from 1,000 all the way down to 524.881. The market looked like it had lost half its value. But the underlying stocks were performing fine.
Right.
It was financial death by 100,000 paper cuts.
The paper cuts compound. And this is, I cannot stress this enough, the single most important lesson for anyone taking a high-stakes exam.
Yes, listen up.
You must carry extra digits through the intermediate steps of your problem. You only round the final answer.
Because if you round at step 1, step 2, and step 3 of a complex dosage calculation...
You are compounding your errors. You are basically Vancouvering your own test score.
Vancouvering your test score. I love that. And that brings us to another massive systemic failure from the sources, NASA's Mars Climate Orbiter in 1999.
That one hurts to talk about.
A $327 million spacecraft that just disintegrated in the Martian atmosphere.
And the root cause of the loss was a unit mismatch. A subcontractor software calculated thruster force using the imperial unit of pound-seconds.
But NASA's navigation software, which received that data, was expecting the metric unit of Newton-seconds.
Exactly.
Now, while that isn't technically a rounding error, it is the ultimate argument for estimation as a sanity check.
Absolutely. The conversion factor between pounds force and newtons is roughly 4.45. The navigation data was off by a factor of nearly 4.5. If a single engineer had applied a Fermi-style order of magnitude estimation, just roughly scaling the numbers in their head, they would have looked at those trajectory readouts and realized the input was fundamentally impossible.
Wow.
The precise calculations were flawlessly executed, but they were executing the wrong reality.
So what does this all mean for you, the learner? We're talking about billion-dollar space probes and stock exchanges, but if you're taking the TEAS or HESI exam tomorrow, the stakes are sitting in a hospital bed.
Yeah, the application of this in daily clinical practice is deeply, deeply human.
The patient safety literature heavily documents medication errors involving misplaced decimal points.
Heavily. In clinical pharmacology, a single shifted decimal doesn't just mean the medicine is slightly off. It almost always results in a 10-fold overdose.
10 times the amount. One tiny dot on a page separates 2.0 milligrams from 20 milligrams.
Which is why the core protective habit, taught in nursing math, is the estimate first rule. Before you ever touch a calculator to compute the exact weight-based dose for a patient, you estimate what a reasonable dose should roughly be.
Right, so if your mental estimate tells you the volume should be around 2 milliliters, and then your exact calculation spits out 20 milliliters.
Your brain immediately flags the discrepancy.
The estimation acts as the safety net.
Exactly. It catches the calculation error before the drug is ever drawn into the syringe. You aren't giving the patient the estimated dose, obviously. You're giving them the exact computed dose.
But you're only giving it to them because your estimate verified that the computation wasn't completely unhinged.
Right. And this is where we run into a major misconception that these exams just love to test. Students often conflate precision with accuracy.
Oh, yeah. They assume a highly precise number is automatically an accurate one.
But they are very different things.
Right. Precision is just how fine your measurement is, like how many decimal places it goes out to. Accuracy is how close that measurement actually is to the true value in reality.
Exactly.
I mean, I can measure the length of my desk out to 10 decimal places, but if my tape measure is fundamentally broken, my answer is just very precisely wrong.
Precisely wrong. I love that. Rounding deliberately reduces precision to make numbers manageable. It never improves accuracy,
Right.
but it allows you to manipulate the numbers quickly enough to verify that your highly precise calculation is actually accurate.
So to boil it all down, here are the 5 exam-style takeaways you need to lock in. Number 1, round, only the final answer, never the intermediate steps.
Right. Don't Vancouver your score.
Number 2, estimate before you calculate. Number 3, remember that rounding reduces precision on purpose. Number 4, know multiple strategies like clustering and compatible numbers so you have flexibility.
Essential.
And number 5, use estimates as safety checks in clinical math. If you do this, you are building an operational defense against catastrophic errors.
You protect your test score, and eventually you protect your patients.
You bridge the gap between Archimedes trapping pi, Enrico Fermi measuring a nuclear blast with paper scraps, and a nurse verifying a critical dosage on a busy floor. Trading precision for simplicity isn't a mathematical flaw, it's a deliberate, powerful choice.
It really is. It completely changes how you interact with information.
It really does.
And, I think about this a lot. We live in a world where we are constantly bombarded by digital screens feeding us highly precise numbers.
Oh, everywhere.
Your smartwatch gives you a heart rate to the exact beat. A digital thermometer gives you a temperature to the second decimal place. A GPS gives you an arrival time down to the minute.
They look so official.
The screen's project authority. But the next time you look at a highly precise readout, ask yourself if you are passively trusting the machine's precision or if you are actively using your own estimation skills to question its accuracy.
That is a great point.
Have we become so addicted to exact numbers that we've lost our human instinct for when a value simply looks wrong?
Man, that is something to think about. The goal isn't just to have the exact key to open the vault door. The real superpower is standing back, looking at the building, and having the instinct to realize you're at the wrong bank entirely.
Exactly.
Well, thank you for joining us on this deep dive. Keep questioning the numbers around you, keep estimating, and we'll catch you next time.